Good morning, viewers, and welcome to the third Form 1 topic, which is acids, bases, and indicators. I am Sungutti Albert, and I welcome you. So, before we go into discussing the acid, bases, and indicators, you have come across substances such as lemon juice, you have come across sour milk, you have come across wood ash solutions. All those substances are edible substances. That is, they can be eaten, they can be consumed by human beings. You find that lemon substances such as lemon juice and sour milk, they have that sour taste. The sour taste is due to the presence of acids. The wood ash solution and even sodium carbonate, which we call Magadi soda, has a bitter taste. The bitter taste is due to the presence of bases. Now, we can define an acid as any substance with a sour taste. Any substance with a sour taste. So, acid is any substance with a sour taste. Any substance with a sour taste. That one is an acid. And a base is any substance with a bitter taste. Any substance with a bitter taste. Any substance with a bitter taste. That one is a base. But we see that so many substances exist in nature, and also some of them are edible, others are inedible. So we cannot use taste as a means of classifying acids and bases. Taste is not an accurate method because some of the substances are inedible, some are poisonous, and others are even more than just besides being poisonous, some of them are corrosive. For instance, you cannot taste hydrochloric acid and say, this hydrochloric acid is bitter, even if hydrochloric acid is present in your stomach. You cannot also taste nitric 5 acid and say, this nitric 5 acid has a sour taste, therefore it is an acid. Or sodium hydroxide has a bitter taste, therefore it's a base. So we therefore now calls for the other substances which can help us to classify the substances as acids or bases. These substances that are used to classify other substances as acids or bases, we call them indicators. Indicators. So indicators are substances that are used to classify substances as acids or bases. And we can define an indicator as a substance which shows a specific color in acid, a substance which shows a specific color in acid and a different specific color in base, a different specific color in base, a different specific color in base. So that is how the indicators classify substances as either acids or bases. That is, all solutions of acids will show a specific color, while all solutions of bases will show a different but specific color from the one for acids. So we are going to go through various types of indicators. So we have various types of indicators. The first one is indicators made from flower extracts. Indicator made from flower extracts. So we are going to look at the indicators made from flower extracts. We look at their advantages, their disadvantages, and then we proceed to the next type of indicator. So the flower extracts we refer to are the flower petals. flower petals. So these are the flower petals. So for you to make an indicator made from flower extract, you take flower petals and put them in a mortar. Put them in a mortar and crush them using a pestle. Put them in a mortar. This is a mortar and this is a pestle. So you crush those flowers using a mortar and pestle. Then you add a solvent. It can be ethanol or propanol. So I am going to add propanol. So I add propanol as I continue crushing these flower petals. Now, you see this ethanol, propanol. The propanol I've used is colorless. But the indicator that I am obtaining from these flower extracts after crushing, it has some color. It looks brown. So that is an indicator that we have made from flower extracts. Now, to prove that this is an indicator, I'm going to use various solutions of acid and various solutions of bases to come and see where they will show a different color in acid and a different specific color in base. So here I can put this one, I put the acid first. Let me use hydrochloric acid. I'm going to use 2 acids and 2 bases in each case. So here this is a solution of hydrochloric acid. So I take hydrochloric acid and just add a little of that indicator made from flower extracts. You see the color that one is going to show. I take a solution of propanoic acid, then I add the indicator. So you find that the color of the solution, the color of propanoic acid and the hydrochloric acid, they show the similar colors. They show the same color. Let's have an example of sodium hydroxide and ammonia solution, which are examples of solutions that are basic. So I have sodium hydroxide solution, and I'm going to use the same indicator for this sodium hydroxide solution. So you see, it is going to show a different color from the one that it had shown for acid. Let me use this ammonia solution also as an example of base, ammonia solution. So ammonia solution, I add the same indicator there. So I see you realize that they will show similar color in base and similar color in acid. Therefore, those ones, that is an indicator that is made from flower extracts. You can see they show specific color in acid and a different but specific color in base. However, we notice that these flower extracts, the indicators made from flower extracts, because the solvent used in preparing the extract is volatile, that is, it keeps evaporating with time, the composition of the indicator varies with time. The composition of the indicator varies with time. Therefore, it does not give consistent results. The color of not just the indicator, but the solutions also keeps changing with time. I will wait for like 5 minutes and try to do the same test for the acid using the same indicator and a base using the same indicator. You will find that the color that it will show in acid and the color that it will show in base will be different from the colors that they had shown previously. So that shows that you cannot rely on it because, for example, this one looks pale green and this one, it looks, we can say, which color is this? Can we say it's pink? Yeah, this one looks pink, this one is pale green. Now, for some time, after some time, when you use the same acid and the same base with that indicator, you'll find that it will not give a pale green color for base and it will not give a pale green color for acid. Therefore, this brings a situation, a state of confusion. So it means that we can only be able to use indicators made from flower extract only when they are fresh. When they are freshly prepared, you can be able to use them. But when they stay for some time, you find that they will not give the same results. I will do that. Let me preserve this indicator, and then I'll prove that point of mine as we proceed. So, indicators, we see that these indicators, they can only be used when they are fresh. When they are fresh. Yeah. So it means they give inconsistent results with time. They give inconsistent results with time. With time. So by saying inconsistent results, we mean they will give different colors. Different colors for the same substances. For the same substances. They will give different colors for the same substances as time goes. So that one is being inconsistent. A good indicator should give consistent results. That is, if the solution is acidic, whether I test it this morning, tomorrow, the following day, it should give me the same color. If the color does not resemble the one that has been shown previously, then it means that that indicator is not consistent. So, for consistency, we have indicators which we call commercial indicators. Commercial indicators, there are so many types of commercial indicators, but we are only going to deal with the 3 commercial indicators. So number 2 is commercial indicators. Commercial indicators. These ones, they give more consistent results. They give consistent results. That is, they will show the same color in acid and the same color in base. Then there are 3 types of commercial indicators. So we are going to discuss that bit by using a table. So the indicator, I'll write the name of indicator here. Then we have color in acid. Then we have color in base. So let me put it that way and put a heading here, color in. So I start here, acid, base, and then we have some substances which are neither acidic nor basic. Not all substances are acidic or basic. They have some substances, they are not acidic, they are not basic. Such substances which are not acidic or basic, we call them neutral substances. So an example of neutral substances, we have water, distilled water, which I have with me in the wash bottle. I also have common salt, a solution of common salt, which we call sodium chloride. So we have 3, as I said. The first one is litmus paper. Then we have methyl orange indicator. Then we have number 3, phenolphthalein indicator. So we are going to fill in this table by doing some small demonstrations here. So let me start with litmus paper. Let me start with litmus paper. Litmus paper comes in two colors. We have the first one, which is blue in color. This one is a blue litmus paper. This one here is a blue litmus paper. We have another color for litmus paper, which is red. So litmus paper is mainly brought in two colors. We have one which is blue, and we have one which is red. So let me start with a solution of hydrochloric acid. Solution of hydrochloric acid. Solution of hydrochloric acid. Let me see the color that litmus paper is going to show in a solution of hydrochloric acid. So I'll just dip the litmus paper inside there so that it meets that. So you see that a solution of hydrochloric acid, the litmus paper changes from blue to red. This was the color of litmus, it has changed to red. So it shows that litmus paper is red when the solution is acidic. Litmus paper is red when the solution is acidic. So this solution of hydrochloric acid, we have said the litmus paper is red. Let me have a solution of nitric acid also, because we need to see whether it's going to give consistent results. So let me use the same blue. Having seen that in a solution of hydrochloric acid, the litmus paper is red, let me find out with this one whether it's also going to turn red. So you see, the litmus paper turns red. The litmus paper turns red. Litmus paper turns red there. Let me have another solution of propanoic acid. Let me have a solution of propanoic acid and see whether the litmus paper is also going to turn red. So this is a solution of propanoic acid. I add that propanoic acid in a test tube and then take the red. So red litmus paper with the propanoic acid. Yeah, you can see the litmus paper has turned red. So it means that for litmus paper, if the solution is acidic, if the solution is acidic, the litmus paper will turn red. Let me see for a red litmus paper, just for the sake of it, is litmus paper, red litmus paper going to change? Now we can have hydrochloric acid. Hydrochloric acid, you see the litmus paper remains red. It does not change from blue to red. Hydrochloric acid, litmus paper remains red. But if the litmus paper is blue, blue litmus paper turns red. Let's have a solution of a base. Let me use sodium hydroxide. Sodium hydroxide. Sodium hydroxide. So sodium hydroxide solution here for blue. Let me start with blue litmus paper. Blue litmus paper for sodium hydroxide, you can see that the blue litmus paper remains blue, while red litmus paper, let's see for red litmus paper, red litmus paper, so you can see red litmus paper turns blue. So it shows that the color of litmus paper in acid, litmus paper in acid, the color is red. In base, the color is blue. Let's see in a neutral substance like distilled water. A neutral substance like distilled water. So I'm going to use both red and blue. So you can see here in distilled water, the red litmus paper remains red in distilled water. Red litmus paper remains red. While, let's see blue, whether blue litmus paper is going to turn red. Blue litmus paper remains blue. So red litmus paper remains red, while blue litmus paper remains blue. Red litmus remains red, while blue remains blue. Blue litmus paper remains blue. We don't say there is no change on the litmus paper. We cannot observe nothing. There is nothing like there is no change. We cannot observe no change. We can only observe that the paper is not, the color of the paper is not changing, but we cannot observe no change. That is litmus paper. There is the next indicator, which is methyl orange. I have methyl orange indicator. I'm going to use a solution of an solution of an acid. So you see the solution of propanoic acid, which I had put here, the solution of propanoic acid. Yeah, you see that the methyl orange indicator shows a pink color in acid. Pink color in acid. Methyl orange will show pink color in acid. What about a solution of sodium hydroxide? Or let me use ammonia solution. A solution of ammonia solution. So methyl orange in ammonia solution, you see it becomes yellow. The color is yellow. Methyl orange in a base, the color is yellow. Then methyl orange in a neutral substance. Methyl orange in a neutral substance, like distilled water. Let's see the color of methyl orange in distilled water. Let me rinse the test tube first. It looks to be contaminated. So you see, in a neutral substance, methyl orange is orange in color. Orange in color. It's not yellow. Orange in color. It is orange. In a neutral substance, it is orange. Let me test using another neutral substance. We have said sodium chloride. Sodium chloride solution. The same methyl orange, you see, it is orange. Orange. Methyl orange. Methyl orange. The color is orange. So in acid, it is pink. In base, it's yellow. And in a neutral substance, the color of methyl orange is orange. Now, let's see phenolphthalein. I'm going to start with ammonia solution, which is an example of a base, phenolphthalein. Phenolphthalein. So this is phenolphthalein indicator. So I'm going to use it to classify the substances here. So you can see that one, phenolphthalein in ammonia solution, which is basic, ammonia solution. Phenolphthalein in a base is pink. Phenolphthalein in a base is pink. Even if I use sodium hydroxide, let me use sodium hydroxide, which is an example of a base. Sodium hydroxide, sodium hydroxide. Phenolphthalein indicator with sodium hydroxide, you can see it shows the same color, pink. So in a base, it is pink. But in an acid, let us see, like this acid, I had used litmus paper. Let me use a different test tube. So in an acid, the color of phenolphthalein indicator is colorless. The color remains colorless. The color in acid is colorless. Color in acid is colorless. Color in neutral, we want to see a neutral substance, the color in a neutral substance. Color in a neutral substance like sodium chloride. Phenolphthalein indicator in a neutral substance, we see it's colorless. It's colorless. Colorless. Phenolphthalein in a neutral substance is colorless. So those are the colors that the commercial indicators will show, both in acid, base, and in neutral substances. But you see here, all the acids will show a similar color. All the bases will show a similar color when you use them with those indicators, the commercial indicators we have seen there. Solution of hydrochloric acid, solution of nitric acid, solution of sodium hydroxide, ammonia solution, distilled water, and sodium chloride. They will show the same color when we use all those indicators we have stated above. But we know that not all those solutions are the same. We have some acids and bases that are stronger than others. Some acids and bases are stronger than others. So these commercial indicators, the disadvantage they have is that they will only classify. So commercial indicators only classify the substances. Only classify the substances either as acids or bases, either as acids or bases, but do not give more information about their strengths. So they will just classify the substance as acid or base, but will not give information about their strengths. So, as we have said that strong acid and acid will just show one color, like propanoic acid and hydrochloric acid. They will show the same color in litmus paper, the same color in methyl orange, the same color in phenolphthalein indicator. Sodium hydroxide and sodium carbonate ammonia solution, they will show the same color in litmus paper, same color in methyl orange, same color in phenolphthalein indicator. But then we know that they are not the same in terms of the strength of the acids or bases. So the commercial indicators will only classify them. They will give the two extremes. That is, it is either an acid or it is a base. But it does not provide more information about the strength of those acids or bases. So to give more information about the strength of the acid or bases, we use what we call universal indicator. Universal indicator. So indicator number 3 is universal indicator. And the universal indicator is just a mixture of indicators, several indicators. Universal indicator. Number 3 is the universal indicator. Universal indicator. Universal indicator, we have said that it is a mixture of several indicators. A mixture of several indicators. And we see that this one, it not only not only classifies the substance, it not only classifies the substance as either acid or base, but also gives information about the strength of the substance, gives information about its strength. How does a universal indicator give information about the strength of an acid or base? The universal indicator does that because it comes with a range of colors. It comes with a range of colors. Which are arranged in a scale called P, small p, capital H, called pH scale, the pH scale. So the pH scale has values. The scale has values from 1 up to 14. Values from 1 up to 14. The values from 1 up to 14 are what we refer to as the pH values. The pH values. So the pH values from 1 up to 14. pH is simply the degree of acidity or alkalinity of a solution. The degree, the extent of acidity or alkalinity of a solution. So in between there, we have a pH of 7. So any substance which is acidic, it has pH less than 7. So pH below 7 is acidic. pH greater than 7 is basic. So pH greater than 7 is basic. So any pH value greater than 7 is basic. So we say is basic. Then this one we say is acidic. So we have 1, 2, 3. Let me make this scale 6, 5, 4, 3, 2, 1. Then here 8, 9, 10, 11, 12, 13, 14. So 14. So 8, 9, 10, 11, 12, 13, 14. Therefore, any substance with a pH greater than 7 is basic, pH less than 7 is acidic, and a substance with a pH of 7 is neutral. pH of 7 is neutral. So the range of colors are usually shown on a pH chart. The range of colors are usually shown on a pH chart. So solutions of strong acids have got pH ranging between pH 1 and pH 4. Weak acids between just after 4 up to just before 7. pH just before 7. Then just after 7 up to around pH 11, they are weak bases. Then strong bases start from just after 11 to 14. So I can say this is strong base. This one here, up to somewhere here, is weak base. Then just before 7, up to around there, this one is weak acid. Then from pH 1 to pH just around there is strong acid. So it means when I'm coming from pH 7 going towards 1, I'll be increasing acid strength, because this is weak and this is strong, so we are increasing the strength. Weak, strong base. So increasing strength of base. Increasing the strength of base. So we want to see how we can be able to find the pH of a solution. So in order to find the pH of a solution, you take that solution, like this is a solution of hydrochloric acid. Then you add few drops, 2 or 3 drops of universal indicator. This is universal indicator. You add few drops of that universal indicator and then check the pH of that solution using a pH chart. So you match the colors using a pH chart. So you see here, this one has a pH of 1. pH of 1. So hydrochloric acid has a pH of 1. It shows that that one is a strong acid. Let us see a solution of acetic acid. Acetic acid. Acetic acid. Acetic acid. Let me add acetic acid. So you see the solution of acetic acid is different from that one for hydrochloric acid. So acetic acid here, we see it has a pH of 5. pH of 5. So acetic acid, pH of 5. So it shows that the pH of 5 is a weak acid. Let's see ammonia solution. Ammonia solution. Ammonia solution, put some universal indicator with that ammonia solution. So you check the color of that ammonia solution with the color on the universal indicator. You see that it is akin to that one of pH 9. pH 9. So pH 9. pH 9, we have seen, is a weak base. So ammonia solution is an example of a weak base. Let's use sodium hydroxide. Sodium hydroxide solution with the same universal indicator. Sodium hydroxide solution with the same universal indicator. You find that this sodium hydroxide, it has a pH of 14. pH 14. pH 14, we have seen it's a strong base. So examples of strong acids and bases. So examples of strong acids and bases. Examples of strong acids and bases. So examples of, let's say, number 1, strong acids. Strong acids, we have said one is hydrochloric acid. We have seen it, in fact, it has a pH of 1. We have nitric 5 acid. Nitric 5 acid. We also have sulfuric 6 acid. Sulfuric 6 acid. Sulfuric 6 acid. Those are examples of strong acids. Number 2, weak acids. Weak acids. We have seen the one for pH 5 was acetic acid. So we can have acetic acid. We can have lemon juice, which is citric acid. We can have propanoic acid there. Propanoic acid. And these acids, they have a common name, which we call them mineral acids. So mineral acids are strong acids. These ones have a common name, which we call organic acids. The organic acids are solutions of weak acids. Let's look at the examples of strong bases and weak bases. Examples of strong bases and weak bases. So number 3, strong base. Examples of strong bases. 1, we can say sodium hydroxide, whose pH we have seen is 14. We have potassium hydroxide. Potassium hydroxide. We can also have lithium hydroxide. Lithium hydroxide. Those are examples of solutions of strong bases. Then we have, all these should be solutions because you cannot get the pH of, let's say, sodium hydroxide pellets. The solid, you will not be able to get the pH because it will not mix with the universal indicator. So examples of weak bases. Examples of weak bases. We have ammonia solution. Ammonia solution. We have wood ash. And then we have sodium carbonate solution. Sodium carbonate solution. Those are examples of strong acids, strong bases, weak acids, and weak bases. We have said that a substance that is neither acidic nor basic is a neutral substance. So let me see, find the pH of sodium chloride. This one here is sodium chloride solution. I want to get the pH of that sodium chloride solution. pH of that sodium chloride solution. So you see, this one is green, pH 7, pH 7, the green color there, pH 7. Sodium chloride solution, pH 7. I can also have another one, which is distilled water. Let me use the wash bottle. The water that is in this wash bottle. Distilled water in a wash bottle. Distilled water in a wash bottle. You see, the distilled water, it also shows a pH of 7. Green, pH 7. So, examples of neutral substances. Examples of neutral substances. Examples of neutral substances. Number 5, neutral substances. Neutral substances. We have said sodium chloride solution. We have said distilled water. We may also have sugar solution as an example of neutral substances. Sugar solution, sodium chloride solution, and distilled water. Those are examples of neutral substances. So let me go back to this other part for the flower extracts, just to find out whether they are going to give consistent results as we had said previously. So, yeah, it has not changed. This is a base, the color of sodium hydroxide. But you can see the color, this color has changed. It's not the way it was at the beginning. The color has changed for this one. So that's why we say that the indicators that are made from flower extracts do not give consistent results. So today we have looked at the acids and bases, and we have said that an acid is any therefore is any substance with a sour taste, and a base is any substance with a bitter taste. We have said that, however, we cannot use taste as a way of classifying acids or bases because some of these substances are poisonous. Therefore, it calls for the existence of other substances that can help us to do that classification. And we have called them indicators. We have looked at indicators from flower extracts. We have also seen the commercial indicators, which are litmus paper, phenolphthalein, and methyl orange. We have seen the various colors they are going to show in solutions of acids, solutions of bases, and also in neutral solutions. We have seen that the disadvantage with the flower extracts is they can only be used when they are fresh. When they stay for some time, they will give inconsistent results. The advantage for the commercial indicators is, although they are going to give the consistent results, but although they give the consistent results, they cannot be able to give more information about the strength of the acid or the strength of the base. And we have seen that is the main role that is played by the universal indicator. The universal indicator has helped us to classify the substances further, not just as acids and bases and neutral, but also in terms of their strength. Therefore, we can summarize by saying an acid is, let me use a table, this way an acid, and this way a base. So an acid, we can define it as any substance with a sour taste, And a base is a substance with a bitter taste. Substance with a bitter taste. An acid as any substance with pH less than 7, and a base is a substance with pH greater than 7. An acid is a substance which will turn litmus paper from blue to red, And a base as any substance that will turn litmus paper from red to blue, An acid is any substance that will turn methyl orange to pink. Any substance that will turn phenolphthalein, that will turn phenolphthalein to colors, or let me say that will be colorless. It will be colorless in phenolphthalein. Then here it will turn methyl orange to yellow. Turn methyl orange to yellow. And here it will turn phenolphthalein to pink. Turn phenolphthalein to pink. Any substance that will turn phenolphthalein to pink, that one is a base. So we have classified the acids and bases in that manner. So in our next lesson, we are going to look at the various properties of acids and bases. So I wish you all the best.